Welcome to Pavinars, webinars for the pavement community. We're going to be discussing how we can correlate field performance to laboratory dynamic modulus from indirect tension and torsion bar. In brief, the objective of this research was to take 10 different field sections and look at their performance and then try and correlate that to two different laboratory tests for dynamic modulus, the indirect tension test and the torsion bar test. Now this is based on work that Dr. Shu Yang performed toward his dissertation, and the full title of the paper is Correlating Field Performance to Laboratory Dynamic Modulus from Indirect Tension and Torsion Bar. Dr. Yang obtained his Bachelor's of Science in Civil Engineering and his Master's of Science in Highway and Railway Engineering from Southeast University in Nanjing, China. He obtained his Doctorate of Philosophy in Civil Engineering in 2016 from the University of Arkansas, and a link to his LinkedIn profile can be found below in the comments section. So to start with, we're going to go over a dynamic modulus, the who, what, where, when, and why of dynamic modulus. So the dynamic modulus is the ratio between the stress amplitude and the strain amplitude. So the stress amplitude is sigma naught and the strain amplitude is epsilon naught. And this is measured either by axial loading, which is E star, or shear loading, which is G star. How are E star and G star calculated? Well, they're often calculated by a combination of the storage or elastic modulus, which is G prime, and the loss or the viscous modulus, which is G double prime, and that can be correlated and compared to the phase angle. So for example, if we have our G prime on the x-axis, the storage or elastic modulus, and the G double prime, the loss or viscous modulus, you can take the resultant vector of those two moduli and you can get G star. And G star and delta are defined by the corresponding vector and resultant angle between the storage and loss modulus values. Now, what can dynamic modulus do? It can characterize stress-strain behavior, and it can simulate loads from both traffic and the corresponding deformations from that traffic. It's also a primary input into various numerical models, including multiple viscoelastic continuum damage and other constitutive models, and also the largest is the AASHTO Pavement ME. Dynamic modulus is a key input to all of these numerical models. And what we're going to focus on specifically is AASHTO T342, which looks at calculating the dynamic modulus from a uniaxial test method, and then the corresponding AASHTO standard R62, which looks at the analysis of the data from the dynamic modulus test. So R62 in particular, the title of this standard is the Standard Practice for Developing Dynamic Modulus Master Curves for Asphalt Mixtures, and the uniaxial configuration, which is shown in the picture, is the most common way to capture this data. Now, something that should pop right out at you, however, is it's very difficult to get a sample like this from the field because of the size of the sample itself is not conducive to the size of the layers that are placed in the field for asphalt concrete. But at this point, let's just talk about the uniaxial configuration being the most common. And according to AASHTO R62, you collect your modulus data at various temperatures and frequencies. So the temperatures go from minus 10 degrees Celsius to 54 degrees Celsius, and there are 6 frequencies from 0.1 Hertz to 25 Hertz. And what's interesting here is the frequencies are usually determined by the capabilities of the equipment you're using. So unless you have some very, very highly specialized equipment, it's difficult to collect data outside of these frequencies. So what we do is we collect these frequencies at all of the temperatures and we can construct a master curve, which is what we'll go over here shortly. And in order to construct this master curve, we use the concept of time, temperature, superposition. So this concept of time, temperature, superposition is very important. And that is because viscoelastic properties, and asphalt concrete is viscoelastic, is a function of both time and temperature. And as I mentioned, it's difficult to measure properties for either very long times or very short times. But luckily, asphalt concrete is thermorheologically simple, and that means that the effects of time can be replaced or shifted by temperature. And these shifts are represented by shift factors to form a master curve. So lots of information going on here. Let's take a graphical look at what's going on. Now, this is just a 3-temperature example. The R62 standard has 5 temperatures, and it's the same concept, but for brevity's sake, we're just looking at 3 temperatures. And also, I'd like to thank Dr. Ishan Dawe of the University of New Hampshire for these graphs. But what we have here is we have our 3 temperatures. We have -10, we have 21 degrees Celsius, and we have 54 degrees Celsius. And we can see right here that colder temperatures, colder testing temperatures equal a stiffer mixture. And you can see that the frequency we're measuring goes from 0.1 to 25 Hertz. So the modulus is on the y-axis, and higher moduli occur at colder temperatures. And then the frequencies are on the x-axis, and the frequencies we're measuring are from 0.1 to 25, but we're measuring them at multiple temperatures. So if we have these 3 curves, how do you create a master curve? Well, what we do is we shift 2 of the temperatures. So here we have T3, T reference, and T2, and we shift T3 and T2. And we do that by a shift factor. So we take our frequency and we multiply it by a shift factor in order to get what we called a reduced frequency. So if you keep your eye on the T3, the top line, we multiply it by a shift factor and it moves over to the right. Now the same thing happened on the bottom, except it moved to the left, and what you get is one single curve, and that is your master curve. And you can see this curve goes from approximately, if you're doing the shifting correctly, about 1 times 10 to the negative 8th reduced frequency up to 1 times 10 to the positive 8th reduced frequency. And this curve, which is now the highest testing temperatures on the far left and the lowest testing temperatures on the far right, the shifted continuous curve is known as a master curve. So it seems relatively straightforward, but how do you go about calculating this master curve? What sort of calculations do you go through in order to construct this master curve? Well, we use a sigmoidal function, and there are 4 fitting coefficients in this sigmoidal function: alpha, beta, delta, and gamma. So the sigmoidal function you can see is the log of the dynamic modulus equals delta plus alpha divided by that longer term there in the denominator, which has beta and gamma and the reduced frequency in the equation. And we can define the E star as the dynamic modulus, the alpha, beta, delta, and gamma as the fitting parameters or fitting coefficients, and then F sub r is the reduced frequency in Hertz. And there are 2 ways to obtain the reduced frequency. We can either use what are called MEPDG shift factors, according to AASHTO R62, and these MEPDG shift factors are viscosity based. Note that MEPDG stands for Mechanistic Empirical Pavement Design Guide, and that is what AASHTO Pavement ME was called about 3 generations ago of computer programming. But regardless, the MEPDG shift factor is viscosity based, and the second order polynomial is a reference temperature based, which is what we saw on the previous slides. And this study also used the latter, the second order polynomial. But regardless of which one you use, the MEPDG or the second order polynomial, it both involves optimizing coefficients. So how do we go about optimizing coefficients? Well, let's take a look at an example master curve. So this is a second order polynomial master curve, and you can see here we have our various temperatures from -10 degrees Celsius to 54 degrees Celsius. We've shifted them, and then we have a line going through that shifted data. So that line was generated by this equation, and in order to get this line using this equation, we needed to determine what those coefficients were. So we have some initial values for coefficients, for alpha, for beta, for delta, for gamma. And we also have some initial values for the shift factors A1 and A2. And what we do is we choose these initial values of coefficients and then we run through Excel Solver. And what we do with Excel Solver is we try to minimize the difference between that fitted line and what are called the isotherms. And those isotherms are the original data. So looking at the same graph, after we run it through Excel Solver, we get our final coefficients. And the final coefficients you can see here are relatively close to the initial coefficients, but the whole point is to minimize that SSE, or the standard square error value, which here is 0.0165. And that's what Microsoft Solver does, is it takes the difference between the fitted curve and the actual data, and it minimizes that difference so you want as low of an SSE as possible. So we just went through a lot of information, and let's have a quick recap before going into what we needed to do for this study. So recall that the reduced frequency equals the actual frequency times a shift factor. And what we're doing is we're looking for a dynamic modulus, and for the sigmoidal function, involves finding those 4 fitting coefficients and the reduced frequency. We're using the second order polynomial solving technique, which you can see here is the log of the a sub t equals that function there, which you can see is a second order polynomial. And the variable, the x variable is, or the dependent variable is the difference between the reduced temperature and the actual temperature. And what we want to do is we want to minimize the difference between the predicted and the actual dynamic modulus value. And this is what we get our SSE from. So in short, this is what we're trying to do. It seems pretty easy, right? But the case is, it is not always easy. So let's talk a little bit about these initial coefficient values. So as we mentioned, the master curves are found by Excel or other math solver programs. You don't need to use Excel. You can use MATLAB, R, whatever program that you desire. But in order to get these initial coefficient values, the alpha, the beta, the gamma, and the delta, in order to get those 4 values, we kind of have some ideas on what we can go off of. And that's because our sigmoidal master curve has 4 shape characteristics. It has the upper asymptote and the lower asymptote. So as you go into extremely high or extremely low frequencies, you hit some sort of asymptote. It has some sort of maximum slope along the sigmoidal master curve, and it has some sort of inflection point. So these are 4 things that we can look at. So focusing just on the upper asymptote, if we take a look at gamma being positive, the delta value equals log E when the frequency goes to infinity. And that's pretty easy to see, again, when we look at this equation. So if gamma is positive, delta equals the logs of E when the frequency goes to infinity. And that makes sense because in that equation, as the frequency goes to infinity, that denominator goes to infinity. As that denominator goes to infinity, alpha over infinity equals essentially 0. So you have your asymptotic value. It never reaches 0, of course, which is why it's an asymptote. But that is why if gamma is positive, delta equals the log of the dynamic modulus when the frequency goes to infinity. Now, if gamma is negative, you can then solve that equation and shift things around where delta plus alpha equals the upper asymptote. So if we're looking at that upper asymptote of the master curve, we can kind of get an idea of some values of delta and alpha. Now taking a look at the lower asymptote, if gamma is positive, the delta plus alpha equals the log of the dynamic modulus when the frequency goes to 0. However, if gamma is negative, the delta equals the lower asymptote. So you can see some trends here with the upper and the lower asymptote and how we can get some initial potential values for some of our coefficients. So this is for our delta and our alpha values. Now the gamma and the beta are not quite as straightforward, but there are some reasonable ways to start guessing, and gamma you can set equal to -4n over alpha, and beta you can set equal to this equation. And this is just a way to get some initial coefficient values. Now, what are some potential issues with that? So we went over some basic 101 of how to create a master curve. We went over some of the equations. We went over some kind of tricks of the trade in order to get those initial coefficient values. But what are some potential issues that we have? So let's keep in mind, AASHTO R62 was developed with lab compacted samples. And these lab compacted samples have a diameter of 100 millimeters and a height of 150 millimeters. You put an axial load on the sample, which means you're pushing from the top, and you have on specimen strains of 60 to 150 microstrains. And that's so it stays within the linear viscoelastic region. So this is a very, very highly controlled test for these lab compacted uniaxial samples, as we can see here. And this is a very well-behaved test. You can get a lot of good data, and it's relatively insensitive to the initial guess values. Because the data is so well-behaved and because you're able to collect such high-quality data, you really don't get in a whole lot of trouble with those initial guessed values. Now, remember going back to a point I made before, it's essentially impossible to get a sample like this from a field section. And that's because very rarely is asphalt concrete laid in lifts more than 4 inches thick, which is what you would need as a minimum lift thickness. That 100 millimeters thick is the minimum size you would need for a sample. And we very, very rarely place asphalt that thickly in the field. Plus, you would then have a horizontal sample. So it wouldn't even be representative of what's happening when a load goes over a pavement section. So this is not the case for field samples. You have a different geometry, and that is because you have lifts that are usually 2 to 3 inches thick for your samples. So if you take a look at the indirect tension test, you can have a sample that's 150 or 100 millimeters in diameter and 50 millimeters or less thick. So this is very conducive to a single lift for an asphalt concrete pavement. Now, another geometry you can have is the torsion bar sample. And you can see here, these samples are 12.5 by 6.5 by 50 millimeters. Again, something that you can very easily get out of these relatively thin lifts of asphalt that are placed in the field. So this is the good news. We have two different configurations where we could potentially get data for dynamic modulus, either using the indirect tension or IDT, or the torsion bar, which we'll call capital TB. Now, some things to think about though is you have very different on-specimen strains. The strains that we're measuring, as you can see on that IDT, revolve around the center of the sample, so it's an indirect measurement. So that gets a little complicated. And the torsion bar, you're basically just using measurements from the edges of the sample, the very top and the bottom, because there's actually no on-specimen devices to measure the stresses and strains. So you're relying on the equipment that is mechanically affixed to the sample. Now, also, because you have a field sample, you have a very wide range of quality of samples. So as you know, when you're driving over a roadway, there are some roads in good conditions, there are some roads in very bad conditions, and there's some somewhere in the middle. So you can imagine trying to extract a sample like this, you'll get a very wide range of the quality of samples. So this leads to two issues. One is you are more sensitive to those initial guess values. So in the lab, with the lab compacted samples, lab fabricated samples, using that uniaxial testing, it is insensitive to initial guess values. While here in the field samples, you're very sensitive to initial guess values. And another issue is that you can get extremely unreasonable results. So if you just plug your numbers into AASHTO R62, you chug them through solver, you can get some very unreasonable results. So let's take a look at these two issues. And before we get to that look at the two issues, I just want to recap what a master curve format is for this paper, because we're going to be seeing a lot of these graphs and there's a lot of information on here. So you can see we have our modulus on the y-axis, we have our reduced frequency on the x-axis, and we went through how to get those how to make that master curve. We have 5 testing temperatures from -10 all the way down to +54. -10 has the highest stiffness values, 54 has the lowest. And then we have some initial guesses here for our coefficients, our alpha, beta, gamma, and our A1 and A2 shift factors, which is that second order polynomial component. And then we also have our SSE. And our SSE value is what we're trying to minimize in order to get those final coefficient values. So this is the template that we're going to be using to look at almost all of the data here in trying to understand how to capture good shift values and good master curves. So issue number 1, our sensitivity to initial guess values. So for this study, our initial coefficient values were -2 to 4, to +4. And I'm going to show 2 different examples. This top graph here is from AASHTO T62. So you can see our alpha is 3, our beta is -1, and our delta is 0.5. Our gamma is -0.5. Those 4 initial guess values are from AASHTO R62. If you look at that standard, those 4 values are listed and you're supposed to set them to that. Now, we also tried a couple different ones, and this is more from experience. So our alpha was -2, our beta was 0.5, our delta was 4, and our gamma was 0.5. So different than the AASHTO T62, but kind of in the ballpark. So our initial values were anywhere from -2.0 to +4.0. Our final coefficients then ranged from -41.9 to 4.8. But you'll notice that the A1 and A2 were relatively stable. And if A1 and A2 are relatively stable, that means our isotherms of actual data are spaced similarly. And I'll get to what that means in a second. The SSE, which is the difference between the isotherms or the actual data versus the fitted curve, they have relatively similar values. So our actual data, which is the circles, lines up relatively nicely onto the fitted curve, which is the solid red line. But this is from a good condition pavement. So this is kind of a high quality sample that we had. And you'll notice that the reduced frequency is about 15 decades. So it goes from 1 × 10 to the -6 all the way up to 1 × 10 to the +9. So there's about 15 decades of data here. And that's what I mean when I say that the isotherms of actual data are similarly spaced. So we have a little bit of overlap between each isotherm, which is important. And that's kind of how we get our initial A1 and A2 guess values as well, because we want the highest temperatures, the highest testing temperatures to match up with the lowest testing temperature of adjacent isotherms. So the master curves are relatively similar, but you can see sensitivity does exist. And that sensitivity is shown by the pretty wide range of final coefficient values. So this is issue number 1. Issue number 2 is what we call extremely unreasonable results. So this top image here, this is from the previous slide, so it's the exact same data from the previous slide. And we called these reasonable results, and that was about 15 decades of data. So what are unreasonable results? This is an unreasonable result. Now this is also from a good section, but let's take a look at some of the details. You can see we have the same initial coefficients from AASHTO T62. So alpha equals 3, beta equals -1, delta equals 0.5, and gamma equals -0.5. And you can also see the final shift factors appear normal. So nothing looks really terribly off. There's no massive final values that are completely out of reasonable. But take a look at the SSE. The SSE is extremely high. It's 0.186, which is almost 10 times, it's greater than 10 times higher than the SSE from the other data. And that reduced frequency is 50 decades. It goes from 10 to the -25th all the way up to 10 to the +25th. And those isotherms are not overlapping at all. But this is the problem with simply blindly following a standard, because this followed AASHTO T62. We did everything according to the book, And we could have spit this data out because this is what AASHTO T62 told us to do, but looking at the data shows completely unreasonable results. There's no overlap of the isotherms, you have a very high SSE value, and your reduced frequency is 50 decades, which is just tremendously high. So, what do? We looked at two different iterations. The first iteration was new rules based on experience. So we're going to stick with our so-called bad data over the 50 decades and say this was the bad data, this was unreasonable, what can we do? So our first iteration was to input these values. And this is based on experience. So this is just based on work that we've done over the years saying, well, we could tweak those initial guesses and have a little more accurate. So the delta is the maximum log of the dynamic modulus. The alpha is the minimum log minus delta. And then the inflection, we'll set it at -2 and the n at 0.15. So this is based on experience. And we got this curve. So our initial values here of alpha, beta, delta, and gamma, you can see are negative 1.1, 0.8, 4, and 0.4 respectively. And our SSE did decrease, so our SSE went from 0.18 to 0.0126, which is very good. That SSE is comparable with some of the other ones we got. But our reduced frequency is still approximately 24 decades. So there's very large spacing in our isotherms. The actual data are not overlapping at all, which is worrisome. So then what we did is we turned to a Schaefer paper from 2011, and I apologize if I mispronounce your name, but this was from over 500 experiences, and some more limits were established for shift factors. So they went a little deeper into this work. So this is from the previous slide. This is the first iteration. Now we're going to apply some experimental-based shift factors. And that includes the -10, the shift factor should only range from 3.9 to 5.7, and at +54, the shift factor should only range from -2.7 to -4.4. So basically what we're saying here is that you can only shift the data so much. You're putting a bound on how much you can shift. And again, this is based off that over 300 samples from the study in 2011. So this is built off both experience and experiment in a high level of data analysis. And this is the master curve that we obtained with these additional restrictions at -10 and +54. Now, interestingly, the SSE actually increases a little bit, so you have a little worse fit. However, the rationality of the fitting is much better. So our SSE increased, but the rationality of the fitting is much better, and that's because those isotherms are much closer and our reduced frequency only goes across about 16 decades. So this is a much better looking curve. So you can see that our initial guess values remain the same, but we added that barrier of the shift factor coefficient at -10 and at +54. And by adding that barrier, we were able to get a much, much better looking curve, even with a slightly higher SSE. And this has potential implications in the AASHTO Pavement ME and the other mechanistic software. So these are inputs for our modeling in order to model pavement performance over time. So it's very important that we have good master curves that represent the data that we're trying to get. So that is a very, very extensive background on master curves, how AASHTO R62 goes about calculating master curves, and then some of our findings from this research project on how we used a little more advanced analysis techniques in order to get higher quality master curves beyond R62. Now we did all this by looking at 10 field sections, and from those 10 field sections, we got a total of 270 cores. So all 10 field sections were from the interstate in the state of Arkansas. So if you look at this map, Little Rock is in the middle, and then going up to the left is I-40, down to the left is I-30, and then to the right is also I-40. And there were 3 sections off of I-30 in the lower left. All 3 of those were good sections. You can see there's 2 from Well, all three were from Arkadelphia, and those are G1, G2, and G3. Up to the left are 4 sections on I-40, and you can see there are 3 pore sections along here and 1 medium, so P1, P2, P3, and then M2. And then I-40 on the right, going from Little Rock to Memphis, we have 1 good, 1 medium, and 1 pore section, and that's M1, P4, and G4. So lots of different sections here, 10 field sections, but they're all from interstates in the state of Arkansas. And what we did is we took 270 cores, and these cores were huge. It was great. But they all had a top surface, a bottom surface course, a binder course, both the bottom and the top, and then a base course. Now, for this study, for what we did for this paper, we were only looking at those 2 top surface courses. And this was specific mixtures, very high quality. This is the surface of an interstate, so you have pretty much the best mixtures in the state. And there was a top surface course, which is S2, or you might see it as -2, and a bottom surface course, which is S1, and also indicated by a -1, or -1, or -1. So these are both the same mixtures. They both come from the surface mixture of the interstate, but they were laid in 2 different lifts, about 1.5 to 2 inches each. And we called them the top surface course and the bottom surface course. And the top was S2 and the bottom was S1. Now here is an example of some of the final curves. And this came from one good section. This actually came from section G1. And you can see we have a top surface lift, which is indicated by the -2s. And we have a bottom surface lift, which is indicated by the -1. We also have indirect tension, or IDT samples, and torsion bar samples, or TB. So this is one field section with G1. Then we have our top surface lifts, which are dotted lines, and our bottom surface lifts, which are solid lines. And we use 2 different geometries. We used an IDT and we used a torsion bar. And you can see some general trends here. The torsion bar values were always less than the indirect tension values. And the bottom layer values were always greater than the top layers. So these were the kind of 2 biggest findings that we were able to get out of this research. And we'll go into a lot more detail about what this means and how we got it from more extensive data. But this is just an example of a final curve. Now, for the results of this study, just like when we were going through the master curve development analysis, we kind of had a template of how the graphs look. We also have a common template for the results. So you can see here that each data point along here represents a single temperature and a single frequency, and it is an average of 3 samples. So here we have a total of 4 different sections we're looking at, and these are all poor performing sections, P1 through P4, and we have both E star and G star data, depending on the section that we're looking at. And what we did is we looked at, in this graph, the top layer, the top surface layer versus the bottom surface layer. And in theory, if a data point lines up on that line of equality, then there's no difference between the axis parameters. So if your data falls along this line of equality, your bottom surface layer is behaving identically to the top surface layer. However, if the data is below the line, which the majority of data is in this line, this means that the top surface layer was consistently softer or less stiff or had a lower modulus than the bottom surface layer. And you can see it doesn't matter which pore section we looked at or which geometry we looked at. The bottom surface layer always had a higher modulus than the top surface layer. And what we did is, looking at this formatting, we looked at the geometry. So we looked at the IDT versus the torsion bar, we looked at the top surface versus the bottom surface, and then we looked at the field performance. All of them used this type of presentation of data. So let's look at the IDT versus the torsion bar. You can see the IDT is E star, and that is on the y-axis. The torsion bar is G star, it's a shear modulus, that is on the x-axis. And you can see here the IDT is always greater than the torsion bar. So our E star modulus is always greater than our G star modulus. And could this be a function of geometry or the modulus type? These are two different things that could be a function of. And it is not encouraged, it is discouraged to compare between the shear and the compression modulus. So some people are tempted to take for example, the compression modulus, the E star, and convert it to the shear modulus, or the G star, but that's discouraged because in order to do that, you have to assume that hot mix asphalt is homogeneous and isotropic. Unfortunately, hot mix asphalt is not homogeneous and it is not isotropic. So it's very difficult to convert between the E star and the G star values. Another thing that could be going on here is the representative volume element could be violated. So if you recall those torsion bar samples, the G star samples are very small. The biggest dimension is 50, then you have 12.5, then you have 6.5. And when you're looking at the size of aggregates, there is a chance that one single aggregate could take up the entire volume of a cross section of the sample. And then are you testing the mixture or are you testing a single aggregate? So we could have some RVE, or representative volume element violations. Now this is showing for the good sections, but there are very similar trends for the medium and the poor sections as well. Now taking a look at the top surface versus the bottom surface, the top surface of the pavement is weathered and you have surface damage. And when we talk about weathering, that means the mix is hardened and stiffened, and that's due to sun, wind, and oxidation. However, surface damage on the top layer can soften a mixture. So the moisture damage and traffic can actually soften the mixture. So our top layer here is exposed to two different things. It is exposed to both weathering and surface damage. The weathering hardens, the surface damage softens. The weathering increases the modulus, the surface damage decreases the modulus. So we kind of have two different things competing against each other here. And if you look at the literature, the damage in pavement goes anywhere from 12 to 50 millimeters deep. And a lot of research shows it being very high levels of damage in those upper portions. So only the 12 to 25 millimeters deep, but it does go a little further down. And when we think about how these surface layers are laid down about 1.5 to 2 inches thick, that means in theory, all of the damage is just occurring in that top surface layer. And you can see here in this graph that the top is less than or equal to the bottom modulus. And that means the softening mechanisms, so that surface damage of moisture and traffic, is stronger than the hardening. So in theory, the bottom surface layer should not be exposed to either the weathering or the surface damage. Only the top is, and because the top is consistently lower than the bottom, the softening mechanisms are stronger than the hardening mechanisms. So the moisture and traffic is causing more damage than the sun, wind, and the oxidation. And again, these are all just the good sections. There are very similar trends for the medium and poor sections as well. Now finally looking at the modulus versus the field response. So here what we did is we took our modulus values and we just compared the medium sections to the poor sections, both in the IDT and the torsion bar configuration, the E star and the G star, and also the two surfaces, the S1 and the S2. And this is a little more interesting. First of all, there was a relatively strong evidence of rotations. The higher modulus met the expected trends. We expected the medium sections, the better performing sections, to have a higher modulus than the poorer performing sections, and that happened at the higher modulus values. But there's evidence of rotation, so the lower modulus values are actually the opposite. So you can see down there in the decades from like 1 times 10 to the 1 up to 1 times 10 to the 2, the poor sections had higher modulus values, but then looking at the 1 times 10 to the 3 and 1 times 10 to the 4, the medium section had higher modulus. So it's interesting, this kind of rotation that occurred. We're not getting those consistent results. And the good versus the poor, we had decent lab correlation, but you can see here the medium versus poor, and then the good versus medium, we didn't have very good lab correlations. We also felt that the torsion bar was a relatively poor predictor, especially compared to the IDT. And we felt that the pore sections had higher air voids. Well, that was calculated. The pore sections did have higher air voids. And we felt that maybe the torsion bar saw and quantified that a little more in the modulus values. So there's a lot of things going on here, a lot more details in the paper, but I think the major take home is that we really didn't get a clear picture of being able to correlate the modulus values to the actual field response. Now, one last note, we've been talking about good, medium, and poor performing sections. These are all based on the ranking by a former RDOT research division head. And that gentleman had been the division head for over 30 years. He was there for the construction of all these jobs. He was there as those jobs were released to traffic and over the years. And these were simply based on his subjective rating system, but it was a pretty good rating system, and he had the experience in order to quantify things as good, medium, and bad. So in conclusion, looking at field performance versus lab modulus and IDT versus torsion bar, we felt that following AASHTO R62 does not always provide the proper initial values for coefficients, and we discussed some enhanced methods. The IDT values were always larger than the torsion bar. Also, the softening mechanisms are stronger than the hardening mechanisms, so that top surface layer always had lower modulus values than the bottom surface layer, so those softening mechanisms were stronger than the hardening mechanisms. And finally, we felt that relating the field performance to lab performance is not straightforward, and there's quite a few more things that could be explored in that. So again, if you're interested in learning more, you can read the full paper at Road Materials and Pavement Designs. There's the full citation. We do want to thank Shane Underwood, Andrew Hanz, and Gerald Reinke. They did a lot of work with us on this paper. It was definitely a team effort, and we appreciate all their input. And a direct link to the DOI is listed here, and it's also found below in the comment section. So thank you very much for joining us, and I hope that this was an informative presentation.